Hello. Hello. Oh, it's hard to hear. Oh, hello. It's better for you, or you have? Oh yeah, finally. Yeah, yeah. All right, all right, all right. Hello. Okay. No, no, I'm recording. I think there are nobody. Yeah, no, only one participant. So, uh, so just to reiterate, we're basically going over a question from the book that Paul has. Awesome. It's a concept question. Yeah, what? I mean, better. Do you have my email? Or do you want me to give it to you?
So I just
Oh, you found it?
you can also
Yeah, please. So we can see it in here. Which we're showing this. What is it about, the question?
how do you find what the analogy among or summarize with the declaration?
Now, all right. OH book. Oh, like alpha? This thing? This means that, so it will be something like, well, I'm gonna stop sharing. So when you have this symbol, what alpha means when you have a relationship, for example, if you have A alpha B, that means that B it's equal to alpha times some times A times some alpha. What that means is that they are related by a relation factor. So this will be like a parameter you would multiply A by and you will get a B. So they're related by some factor. Yeah. Yeah, it could be. Yeah.
Oh, okay.
So usually when you get that, it's like, oh yeah, they are. You could calculate one from the other by multiplying by the sum factor.
So for in the notes, there's kind of like,
Oh, what do you have? Let's see.
um, well, let's define and
Yeah, closely. So this analogy among energy, mass, and momentum transfer, which can be summarized as the following general relationship. Flux of a quantity being transported times some factor alpha minus the greater quantity being transported. So it's a transport is equal to the flow of what is transported minus the gradient. Okay. So that will be the equals, like transport. No, no, yeah. Yeah. Usually we don't get problems like this. It could be more, usually the type of questions, like definitions, stuff like that, it will be more from the content that we discuss in class. But this it's good that you review this type of things because it helps you understand what we're doing. Yeah. Like this can, yeah, you have an idea what transport means in this context, type of thing. Cool. What you guys have in your homework?
it's not like, you know,
Oh yeah?
and like, you know,
Are you talking about length scale?
yeah.
Or two? Let's see. So it says, question 1 in class, we discussed the two modes of transfer, diffusion and convection. You know what convection? No, what was your question? Continue.
What, like, why is when, just like, why is when still, play, like, from the, like,
Okay.
what, like, where is what?
So you remember when we were talking about Piclet's like number? So basically what we had there is that for some length and with respect to time, no, it's transport time. What it says is that when you have diffusion, in really small length scales, diffusion is really quick. That's what we discussed in class. But it takes a point in which convection is quicker. This point is 100 micrometers. So depending on length scales, you would favor one movement or the other, or you would prefer one transport like manner instead of another. Or for example, if you had
What is it?
no, that's a good question. What? Okay, so length is that's length, and this is the path of whatever this molecule will be transported. So the length is the distance that this molecule is going to travel. That's a good question. because I think that could, yeah, that could, if you don't have that clear, it will be hard to follow afterwards. So yeah, that was a good question. Yeah. So yeah, the length is between from the starting point to the end point. That's the length that they refer to. So diffusion is for small molecules and convection is for big molecules. Yes, but usually when you talk about these things, you try to keep, for example, here's the same molecule, but the difference is the length is traveling. But what you're saying, it's also correct. You would rather use a bigger for bigger molecules, you would use convection or you try to use convection. But I'm not sure about that actually, because you could have like a lot of concentration of one protein in one side and then none in the other side of a membrane. But what depends there is if it's this interface is permeable. And that doesn't have to do it exactly by size, because it could be a really small molecule that is polar. I remember for example, in the cell membrane, we have fat and a phosphorus head. So this is non-polar. So it wouldn't like cross. So a really small molecule like sodium wouldn't necessarily cross this. You need something like a protein to do that. It's good that you're asking this because it's good to have them like sorted out. Like you have to understand them. So yeah, for you, what is convection? What is diffusion so far? Mhm. Okay, that's right. Convection is say the movement is due to a force. Diffusion is movement due to a concentration rate. That's it. Obviously, you can elaborate on those definitions and talking about math and different forces, but yeah, that's. For example, so if I ask you, like, when you're transporting blood within your body, what type of transport is that one? Is it a diffusion or convection? When you have your blood in your system, how and it moves around, does it move with convection or diffusion?
Oh,
All right, and who is applying that? Yes, yes. So that's an example. So if your heart is pumping blood, it's not diffusing blood, it's pumping blood to your system so you can get oxygen in all your body. Then diffusion in your, I was about to say that when you get to the capillaries, then diffusion takes the oxygen from the hemoglobin to whatever is needed, and then the cells can intake it. So it's a combination of both. But in that case, it's really small scale. But the length, it's smaller than 100, so it's better to use diffusion. But when you have meters of in your body of feet that you have to travel, it's different. It's better. So much. That's a concept. Cool. Good, good, good. Good to know. Yeah, yeah, go for it. Path, line. Okay. Okay, let's see. Do you have that in a book? Second question. What are the different information given when you ask assuming velocity, vector fields, path lines, streamlines? We have not touched on that. Is that it?
Well, they probably all in first dimension.
Yes, they all expect. Yeah. Yeah. That's true. Things that in one, things in streamlines is that you are we're gonna go back to this and I'm gonna try to look for my notes, but basically you have like the axis. Then you have one origin. And then your path, streamline. It's like sort of like a family of vectors that you use to create points in your system. And from there, you create a stream in 3 dimensions. And what you're doing here is like in each point, it's a position of a particle. So we're studying particles and their movement. I think this is for streamline, but I need to check. It will be pathline. It will make more sense for pathline, right? But it's one of them. Give me 1 second so I can find my notes.
I think the reported might be that.
Oh, that's okay. Oh, okay. That's okay. Yeah, we did not. Let's see. Yeah, it makes the same makes more sense to be pathline than streamline. Okay. Momentum, fluid kinetic, physical fluid, in time, space, which plane reference. This particle using vectors from text flowing using position vector. I think it's Lagrange. But, yeah, so this is called pathline, I think. And each of these vectors is a position vector. We're studying is a particle and its path. Basically, what you're studying is positions. Yes, I think. Because streamline, it's like more of like it's like a surface. And in this surface, what you have there are vectors, if I remember correctly. And the vectors are velocity. So basically what you're doing there is like every point symbolizes the velocity in that point, and at that place, in that position. That's the difference. Like in one, you're looking more at the particle size, and in one, you're looking more at the whole, like the fluid as a whole, like the flow of the fluid. This one obviously gives you more information, the path line, because you're looking at the position, like how it moves. This one is more like the overall movement of the fluid. But as you can imagine, like knowing all the information from a particle is not that useful. Because you could have a radioactive particle in your body, but that doesn't mean you're gonna die. It's only one atom, let's say. But if you have information how all your blood it's moving, how its profile is going, it's different. That's more information that you can then leverage to know if everything is as it should. Like it's laminar flow, for example, it's not turbulent flow, like Dr. Lewis was saying that having a turbulent flow blood stream is really detrimental for your health, for example. Yeah, transition flows between. Yeah. Okay. You want to review the numbers? I know that Reynolds. So I think at 2100. Can you help me with that? 2100 is something for sure. The other one is I think it's 40 something, 4200.
21 to 4,000.
4,000. Oh, 21 to 4,000. For 4,000. This is transition. Then less than that is laminar flow. Then this is turbulence. All right. Great.
So,
oh, you can barely see this chalk.
oh,
Yeah, that's okay. That's okay. So this one. You see this? No. Well, you're gonna stick to yellow then. All right. Well, actually, I think this is white. Yeah, this is white. This is yellow. All right, I'll do that.
yeah, the first two lines, everything is like that. Each point is like the velocity. One.
Mm-hmm.
Okay.
That position.
Okay.
Let me keep reading my notes and see what else I can. Like for example, there's something called, I think, Evolorian. Can you see that? Yeah. Things like that. Might be wrong, but it's basically that you get a. No, shoot. Oh. So you get this square, or we can imagine a square. What we're doing then is to know, based on velocity, how fluid is going through that fixed volume. We're gonna use this a lot. Oh, that's a window? Oh, my bad. My bad. My bad.
There's a.
Yeah, they are. They are. I'm just didn't know that part. Oh my God, that feels my bad. I didn't mean to do that. Yeah.
Do you want this?
No, I think it's fine because I'm recording like this corner anyways. But yeah, I'm gonna just erase. Thank you. Thanks for letting me know. My bad. Oh, we got into trouble. I guess it's a window. Yeah, it looks like a chalkboard. It does, right? Okay, good. I'm not crazy. I thought so too. But the weird thing is that it has like a shadow that was moving. I was like, is that me? And there's nothing above it. So they were like moving something there, and I saw like a shadow moving. I don't know. That's fun. All right. So, so what else? Yeah, yeah. So you got see if I can do a better job now. Uh, kind of better. Right. Path line over there. Right. Then you get this fixed volume, in which the volume so for example, if we define this as x, y, and z, this length is going to be, well, which is this one, so this length with delta x, this one, delta z, and this one, which has to do with this plane, is delta y. For the volume, they describe it like this. The differential volume is equal to delta x times delta y times delta z. And usually what we try to represent here, it's how velocity like enters and flows through this space. So you have a function of velocity, which is in 3 dimensions. And I'm gonna give you an equation. The average velocity is going to be equal to 1 over a times the integral of average the velocity times, no, this is the dot product of VA. So OSA, yes, scalar. Mhm, mhm. So then here, this thing is, for example, let's say the flow is coming this way. Oh, it's not a good color. Let's see what else I can get here. See blue. Let's say this is the surface that we're using. That surface over there. Which face is that one? Which this one? If you well, so you have y, z, x. We're saying that this is the phase that flow is going through. We're looking for area. The area of that plane. No. So it's so delta x, so it's going in this direction. So yeah. Yes, correct. So you know that A in this case is delta x times delta t. Alright, so we have, that guy. Velocity. Velocity. Velocity vector. Velocity vector is that. You could do that. You could put that here. Let's put that. Sure. Oh, this one I'm gonna leave it for later because I don't remember how it was calculated, but we can definitely do the normal vector. The normal vector is a vector that is perpendicular to the plane they're dealing with. So it'll be something like that. Going from that plane. I think it has to do also with velocity. I know that this vector, what it does is that it defines what the plane is. So like, yes, it is. Yeah, it should be. Yeah, but, I'll say that it's like positive y1, then zero, right? That would be like this vector. Oh, that's sort of falling out to this. Yeah. Like it will be this vector, but this one. Does it make sense? I think that will be that one. I think this is more or less what you guys are talking in that lecture. Have you reviewed it?
Well, I don't think so.
Oh, it's not released yet? It could help, yeah.
I don't. I think.
Let's see what else to talk about. I have like 7 minutes. Yeah, this thing, like the particle thing, was a path line for sure. And the other one was a streamline. Oh, okay. So definition, are you ready? For a streamline. Definition. Thing will be curve tangent to the velocity vector. The one that is going to be more common for you guys is a type of representation that's called the Eulerian. Euler, I think, Eulerian. Maybe L. Or more. Basically, what this is a plot that you guys did in homework 1 is a plot in which you are looking at the velocity profile with respect to position. So, for example, like in homework 1, you can define, put in a system like in the middle of the channel, y, x, and then you give certain values to the velocity in each height. Then you get a curve, the velocity within that channel. And then you have to find stuff like, oh yeah, this length is h, and like this point is 0 centimeters. This one is 1.5, negative 1.5, and that kind of thing. But velocity. Yeah, this velocity. Good question. This one? Yeah, that's sorry. That's y. This is x. Yeah, that's yeah, the orange. Look where it's. There you go. Yep. Feel like a professor, but I'm not sure what I'm saying, but it's okay.
Yeah, I think I'm not to go.
I got to go. All right, my pleasure. Well, we have one student, everyone. Woo! It will be long.